Sure. Thanks a lot, Jousef, and thanks to everyone who have joined to this deep dive. I'm Ram. I'm a solution engineer here at Synera. My background is from computational mechanics, so I was always into simulations. And also, very recently, through a lot of practical experience, I saw where machine learning could help engineers. And I just wanted to share these insights and also show some demos here. And I'm happy to be here along with Jousef.
Very cool. So let's kick things off.
Great. Before we talk about how to solve, I just want to talk about the problems or why we need to think in this direction as engineers. And it's basically because the current status of engineering tools and engineering processes. So right now, a lot of work, especially in hardware product development, work is done sequentially. So it's still a linear process, even though there are a lot of non-linear iterations. The work is done sequentially, especially using expert software. And this means that engineers are split basically into advanced users who know the tool very well, so they have to support a lot, and there forms these silos, CAD designers, then there is the simulation manufacturing. So everyone is split with their own tools, and a lot of this comes with experience. So experienced engineers, of course, have a lot of knowledge in their head, which is hard to put it into paper. And we face these challenges a lot. That's hindering hardware product development, and that's why we think a low-code language meant for engineers is very helpful. So basically, what we try to do is we need to leverage automation. That is, we see what are the manual tasks, what are the repetitive tasks in the product development process, and just automate them. This is the first step to accelerate any product development. And we also have a process canvas in the tool that we see today. It's basically to build your own workflows in a very visual way, which is more closer to the way hardware product development engineers work. And everything is basically like a language. So every step is put into the workflow. There is a language so everyone can read, and there's no need of any expert to use this tool. And cool thing about still being a low-code software is having this powerful 3D visualization, which we'll see in a few minutes.
Mm-hmm.
I want to just show what one of our customer has been able to achieve. So we will also see the application of this or the demonstration of this, but what EDAG has been able to achieve was they saved a huge amount of time in getting their head impact coefficient values. This is basically going through a step of processes, getting the data set, tuning the correct model, and then using this model as a reduced order model. And a lot of customers and users using our tool see a lot of value here. And I would like to then directly show the product. Give me 1 second. Okay, so I would like to show you a short tour of our product to actually give you a feel of how it looks. So as I mentioned, Synera is a low-code software. So there is a editor here where you can drag and drop nodes. You can basically build wires, things like that. And on the right side, you have this powerful 3D visualizer. So unlike traditional CAD platforms, you can't directly go in and build things here. You need to be able to carve a logic here first, and then this will be displayed on the right side. But before we build an actual workflow, I would also like to show you a lot of our nodes that are available. So there are close to 1,700 plus nodes and templates. So each node is basically a kind of a function in itself. So there is a lot about mathematics. There is about data structures, which is essential for Synera. There is also our own CAD creation kernels, so you can build your own curves, surfaces, solid meshes, voxels, do geometry operations like Boolean transformations. And what's powerful is in the same platform, you also have every kind of automation for FEA, and then like additive manufacturing, machine learning, and so on. Recently, we also had injection molding and things like that. So let me show you quickly what building a workflow in synera means. So let's look at something very simple. That's just say I just want to mesh a sphere. So the first thing I need to build is a sphere. So I will just double click the screen. I see if there is something called sphere and there is something called sphere. And the moment I put it in, I see there is an output. So in the way a node works is some inputs come to the left and an output comes to the right. And what I have is a sphere. And now let's say I want to parameterize this radius. So I'm going to say this is going to be a multiplication of two numbers like 5. Again, let me just left drag to see what's available. So number slider. So now you see I just built a sphere and it's parametric. So I can move things here. I get things out there. And now let's say I would like to mesh it. So I would like to go for voxel mesh. And I just plug the CAD into the mesh engine or the voxel mesher. And then the resolution is like the element size, so to say. And then I get the voxel space out. So if I just view this, I see the voxel mesh. So this is, in a nutshell, a process to create a voxel sphere. And these are the parameters through which I can control it. And let's say if I now change certain things, it will work. The whole process will work. And imagine hundreds of steps and you change something, everything else automatically changes. The cool thing is, the reason I talked about expert knowledge is machine learning is something of a special field, and always you can package such complex things into a nice node or a custom node, and then you don't have to really go into it. If you're experts in the department, they worked and built this workflow, you can just automatically use them. So this is about synera in general. So it's very easy to use, simple interface. Really, you can get going just when the day you start. And now I would like to talk about the content or the key topic that we are here for, and that is, as hardware product development engineers, when and why to think about machine learning, because that's a very important question. And we are not usually tuned to this sort of thinking, but the easiest way that I have felt in my personal experience is, if there is some input and if there is an output, and if the way to reach this input to output is usually very hard to find, there is no concrete logic, it's in a very time consuming way, then the machine learning approaches make sense, because there is an input, there is an output, you can map them, and we want to make it as fast as possible and as accurate as possible. And there is no formula that you can just plug it in to get this. So there is no hard coded rule or logic, but still we want to be able to map this relationship. And there are a lot of cases in hardware engineering like this. And before I talk about two examples that I want to show today, I would like to just say what kind of tasks are solvable. And the easiest example I could found was to talk about regression and classification tasks. So it's actually very simple. So a regression problem means you basically want to predict a continuous number. So let's say it's a range of numbers or a specific value. That's basically regression task. So like for example, what will be the temperature tomorrow? It's a specific number. We get that this is a regression task. And classification, the name is pretty simple. And after we get this value, we want to be also able to classify it into one of two categories or multiple categories. So the weather could be cold, hot. Me and Jousef were talking how it's also somewhere in between before we started the session. So so these are the two tasks that's super simple to understand and easy to use for engineers. And this is what, so I personally, when I started, I found always this to be a good starting point. And to draw more, and based on this analogy, I want to show two practical problems that I will demonstrate now. And the first thing is, yeah, a very interesting and very valuable one. So when we as humans look at these parts, we know what these parts are, but it's very hard for a computer to just take in the 3D without any names what it is and then figure out what can it be. Um, Essentially, what we are trying to do is how can we replace the human eye. So the input is basically for humans looking at the viewer, we know, okay, this is this part, and then we usually select it or do some operations, but can we automatically identify this? So we are trying to replace the human eye or lack of information about what that part actually is. And the next classical one is, for example, trying to build reduced order models for FE models. So usually for finite element models or finite element analysis or any simulation setting, there are some input condition, for example, some boundary condition, the geometry parameters itself, and there are some output responses that we want to measure. Like, for example, in structural mechanics, it could be stress, displacement, and so on. Usually, if when we go towards a more system level, this FEM becomes more time consuming. So we need to be, engineers are always thinking of, can I get an accurate result or a reliable result in shorter period of time? And I want to show two things in this direction. So I find these two use cases pretty common in almost many companies that I work with in Synera, and that's why I wanted to show how you can do this in Synera. Yeah, so first I would like to start with the classification task, but before that, Jousef, are there any questions or should I keep going?
Yeah, keep going. Nothing so far, I
Okay,
think.
great. Okay, great. Okay, so yeah, let's start with a classification task. And for any machine learning process, you need always data. And for hardware product development engineers, this is also hard. How can you easily generate data and still make it usable? So I want to show you a simple example of, let's say, I am an engineer working in a bearing company. So, these bearing housing and things like that, and my task is to build a classification model to send in parts and identify what kind of part it is. So therefore, let me just use some of my previous work that I did. So I'm not going to build the CAD now. I will focus more on the machine learning. But let's say one of my CAD engineers working in my team has already built this workflow. So I'm going to be able to use it in an easier way. So let me just go here, pick that I received. So there is a bearing housing workflow that my CAD engineer gave me, and that is basically giving some parameters, getting the bodies out. In the similar way, I want to be able to create a data set of more parts. Let's say I just go here, I use another workflow that my CAD engineer gave. I'm going to use a bearing workflow that also has some um, parameters and gives the body out, and another one to end it, maybe just some simple uh, bolts. That's it. So now what I have is basically three workflows that are parametric, meaning I can plug in some parameters and get these bodies out. So let me just quickly, to make it more time efficient, I'm going to just paste some parameters here, and I can already start plugging them in because I already had them ordered. Uh, so as you see, the moment I plug these values in, I get my body out in the viewer. The similar way, I can also do it for the other. The way I would usually do it is just drag it here, put up a number slider, or make it so, and then I can define a minimum to maximum value here. So we really parameterize these values. So let's say I give it here 20 or things like that, and then I can always vary the distance here. Let me just plug this in. So distance, thickness, and this bearing is going to reference the housing. So the bearing is always going to be inside the housing. So let me just plug that in and give those other two values out here. because it's referencing, and now you see a very rudimentary bearing generated. And a similar way for the bolt, the body would be still the housing body because the bolts go here. And I'd like to reference it with the plate height and maybe give it some distance. Okay, so now if I plug in the right values, you see I get this assembly out. And now my aim is to basically create a data set out of this, and then use it for training and for other things. So the problem is, let's say I'm an engineer working in a department where I have to deal with this geometry a lot, and there are some subsequent tasks which require me to manually classify them, and I'm trying to automate this here. Now, the first thing to do for classification is to basically create classes, and let's just make it simple that this is class 0, this is class 1, and this is class 2. And therefore, what I'm going to do is I'm going to create like a filter, or like that if I pick the right class, I'm going to get my proper filter out. So these are my 3 bodies, and these are my just like a filter to see what's going in, and I can bring in a class index. And if I just view this now, what I mean is, so this is class 0, this is class 1, which is the bearing body itself, and this is the class 2. And yeah, so the first thing that we want to be able to do is, okay, we have the 3D bodies, but what can I do with them? Like, I don't like in machine learning, we need something called features, that is some input to make them trainable. And with geometries, there is actually a lot you can extract. So there are a lot of features, geometrical features that's possible to extract. So let me first put into a block, a geometric container, just to store this data. And what I want to be able to do is get like the geometrical features out. So for example, area, volume, the height, width, length, the height to width ratios, things like this. So these are basically features that are inherent to this body. And as CAD designers or mechanical engineers, we are very used to be working with geometrical features, so that are inherent to this CAD geometry. And that is what we are going to extract. So I already I already prepare my own, let's say, my custom node. So what it basically does is, if I give it a geometry, I can get these features out. So let me just give in my geometry, and you see what I'm getting here is a set of values. And what these are is basically class name, which I will use for training, but also you see volume, area, height, width, length. I can also put a bounding box around it, get the ratio between these two volume, surface to volume, that is area to volume, height to length, height to width, and things like that. So these are my features, and this is how I'm going to identify my parts or train my model. And the way this works is, I can also show you in. So basically, let's say I worked with a CAD designer, and I extracted all these relevant information, and then basically get them out. So this is a custom logic that was completely done in synera. So I'm going to close it now. Go back here. So yeah, this is basically the features, and this is the encoded information that I can use. And let me just plug this in, and basically what I will get is feature values and feature names. Now this was just for one part, and what we want to do is basically create this for each of these classes, for maybe hundreds of such parts, because we want to be able to see, okay, how does these parameters vary over a big range. And that's why I will just filter these values out. So basically, just let me quickly take this in. So I'm just getting from this list, I'm just segregating each of the parameters out. And now what I want to do is basically create a data set. So that's it. So this is basically my data itself. So this is what I will want to train upon. And now I can easily set up a data set. And the way I can do this is I can use something very powerful in Synera called design exploration. So given a set of parameters and responses, I can generate hundreds of designs. I can explore through all of them, extract the responses, and store them. Um, so what I need is I need to set up a parameter setup. Basically, all this would be my inputs. So let me basically link them all. So let me quickly link them. So what I'm doing is right now linking everything there. So what I'm done right now is linked all these inputs. So basically, when I change the class, all the parameters changes. I will just filter each geometry out, and these will be my responses then. So basically, I can just go in and again link these as responses, or easier way would be I just go here. I can go to the setup and basically take everything that's available. Um, that's it. So now I have my parameters that will change, and I have my responses. And to quickly show you, I already prepared a data set of 1,000. It will take close to 20 minutes, and I don't want to do that now. But just to show you how this works, so now I would say create and evaluate, and I would click multiple designs. And there are different algorithms to sample this data. So there is the Latin hypercube, the grid search, the random grid search, and things like that. And now what I want to be able to do, what I would like to do is go for grid design, maybe, yeah, just say, and then I can already click evaluate. Let me just turn on a nice visualizer for now. And yep, and let's just go. So basically, I can then start evaluating, and I can already see the parameters will start to vary. So it's already generating many geometries out now. And what is happening is it's basically generated a set of parameters that it can vary, and we already see that it's starting to uh, get the responses out. So right now it's just sampling a lot of these parameters and working on them. So this is how I can create a data set. So I think I set the algorithm. Maybe let me just stop it. Let me quickly delete them and go for something like random grid search. Yep. So now you see the class index is also varying, and I can quickly evaluate this. So now what I will get is a lot of designs being changed. Um, that's it's visible on the screen. So what it's doing is basically viewing each geometry, taking the parameters out. And let me just quickly bring in my previous data set to save some time.
So what you're doing here, Ram, is basically generating training data for the ML algorithm.
Exactly.
Okay.
Exactly. Yeah. And that is basically extracting the responses based on different inputs. I'm seeing how each body is different from each other.
Mm-hmm.
So let me just stop it here because I don't want to go fully on this. But let's just say I bring in my data set that I trained already. So I'm just going to copy paste from another workflow. And basically what this has is 1,000 designs. And it took me close to 20 minutes to get it done. So it should be as simple as that. And now once I have my data set out, and now starts the real machine learning process, and I want to show you how simple this is. So basically, I also prepared my own set of, so in machine learning, the way we do is we take a data set, we clean up let's say, the features and labels. So we kind of do some data hygiene tasks here. And I'm going to use another node that I created, which basically takes in a data set. I can give these designs out and I get my feature data set and label data set. So I'm just going to plug it in here. And what this is doing in the background is deconstructing the design. It's also doing some cleaning tasks. So if there are null values, I'm just replacing it with them with 0. And I'm just creating some data sets. So basically, just data pre-processing, which is very essential for machine learning. And I just got my feature data set now, label data set. And what's important for classification is to have this normalization factors. And it's very simple to do machine learning training in synera. You just go to models, you just pick the model you want. I'm going to take this multi-class classification. I just plug my features in, I just plug my labels out. That's done. Basically, training is done. And now I want to be able to predict this model. So I'm going to do a model prediction, and this will be my model. So let me just create some kind of sample data. So this could be my sample data, and this is just 3 plots all together. So I have one bolt, all the bearing bodies, and now I want to see if it works to classify them. And basically, let me just list them so that I just pick one of them. Okay, now I just pick one of these bodies in. And now basically I need to normalize this with the factors that I did during training. So I'm going to use convert this into a prediction data first. So this would be this node. And you see here I have a toggle called prediction data. So now when I give the geometry in, I don't need to give it the class index because that's what I want to predict. And basically I get these feature values and names out. Let me now yeah, do this prediction. Yes. Okay. Not this one. Exactly. So what this logic does is basically it takes in this prediction data, uses the normalization factor, and yeah, basically creates a data set for prediction. So I just need my normalization factors. I need the training data set that I used, and then I need the prediction values from the feature, and now I can just predict them. So I have with 4 column, and then I can just extract or deconstruct this data set. So now my initial labels were housing, bearing, and bolt. Now let me just plug this in. So now you see I gave it a housing and it can predict me if it's a housing. Let me just change the body. And this is a bearing. And it's trying to predict, it did predict it's correctly, it's a bearing. And then if I change the index, this is just a bolt and I get a bolt out. So this is how you can very quickly build a classification. I mean, this is just for 3 parts, but what I played here was with this geometrical feature extraction, and in my experience, it works for any kind of CAD model. I mean, any CAD model has these values: area, volume, certain geometrical features. You can always use them to classify parts, and imagine how easy it would be if you have to trigger other processes based on this classification. Right now, I could have only seen this. I should have had the name, or I need to have some kind of other information. But if there's nothing, you can just plug it in so quick, get it in less than a second out, what kind of body that is, and then you can trigger other processes based on this prediction. So this
One
is how
question.
you can, yeah,
Yeah, sorry, Ron, for interrupting. There was one question though. You filled in null values in data
yeah.
pre-processing step. Someone was suggesting, shouldn't it be the mean or mode values of that corresponding feature? Why have you done nil?
Yeah, sure. I mean, this was just to demonstrate, but I can also show you. For For example, I chose 0 because the range was completely different for each of the features, and I wanted to keep it simple. So I did not want to compute a lot of stuff. So therefore, I just saw it ranges from 0.0 to something like e power 6 or e power 9. So even if I fill it with mean, it would seem a bit off, and therefore I had to just make a assumption for this presentation. So I went with 0. But
Got it.
the person who asked the question is right. These things can skew the training a lot when it goes into production, and that time it's simple. So you can just take a average, put the values in, get it out. I mean, this is just replacing one node, so it shouldn't be a big problem. But yeah, this was just my uh, assumption or
Mm-hmm. That
logic
makes
for
sense.
this. Yeah.
That makes sense. Can we actually have a look at the hyperparameters or tune them in the backend, especially for this classification task?
What we can look at, so the reason we have this so simple to use is actually so to make it simple to use. If our intention in the product was to do it like a classic machine learning engineers, then there will be a lot of complex stuff, and we wanted to just boil it down to the simplest. What you can still do is evaluate the model performance. So if you put in the model, then I put in the features, what you can get out is the metrics for this. So these would be my metrics, and these are I think yeah. So I can basically take I have certain accuracies that I can measure. For example, yeah, I forgot to plug the labels, and now you can see the metrics I get, and then also what metrics they are. And you can use them to maybe play with your data set, increase the number of the size of the data set and things like that. And the reason we have it so simple is we wanted to keep it simple. We did not want to overwhelm our users with extremely complex machine learning hyperparameters. But yeah, for example, for the classification, maybe you can find some other logic to normalize this data. Maybe this is the key thing of Synera. You can build your own logics the way you want to manipulate your data, what's best for your task, and then just create these logics like I did. That would be the way to go. And you can always look at your accuracies through model performance.
That makes sense. Pretty cool. I like that. Do you have any other case, like the case that you've shown us, Ram, with the AI prediction? Is it the same way you would approach this problem?
Something that's cool also strikes me from the other question is, so if you're intermediate or advanced or even a beginner and you want to still go with, I don't know, controlling a lot, you can
Yeah.
always plug in your scripts. So if you want to have superior control over your models, of course, the aim would be to go with the um, importing your own scripts, running them in, and then you can also increase the hyperparameters here. So each of this could be a hyperparameter, a lot of these inputs in the script, and you can set up a DOE also for the script, so that you can also automate the way the script optimizes. Um, yeah, and to answer your question, Jousef, one thing that can take this to the next level for 3D data processing is also going to the voxel kernel and just basically looking at each voxel. So let's say there is a bounding box that is like the viewing space. Every time you put a geometry in, it fills in some of these voxels. So we can keep a track of like zeros and ones. And for each voxel it fills, we can train a data. It's a bit complex, but we need it for complex geometry. So we can always extend this logic. We can manipulate this feature and label data set the way we want, and augment the capabilities of this simple workflow.
That makes sense. It's pretty cool.
Yes. Then I hope, this was a small teaser into how classification works in general if you are completely new, and also what is possible in Synera. And now I would like to jump to regression, where we also have some advanced things.
It's
Yeah.
pretty, while you switch from, it's pretty simple though. There is some research going on. I remember when I did my master thesis, there's like people, they try to apply complicated reinforcement learning algorithms to actually detect this kind of stuff. But in synera, it seems so simple. You have a couple of nodes, you connect them. Well, simple in quotations. It's pretty cool.
Yeah, exactly. I think it depends a lot on the engineering task. I wouldn't say this is the only way. So if you're working with some extremely complicated, intricate geometry, maybe, or your data is super widely spread, of course, I would, as a solution engineer, only recommend go for a little bit of, in the sense, tune your hyperparameter, tune your models, build some scripts. But for someone who wants to start, I think this is a great start.
Yeah, absolutely. Yeah. Really cool.